Travis Addair, most recently a technical lead at Uber, and where he led the team responsible for Uber's deep learning infrastructure. Welcome to the Data Exchange podcast.
Hey, Ben, it's great to be here.
So, actually, before we jump into what you did at Uber, two things that for our listeners I found interesting. As I was preparing, I looked at your LinkedIn profile. One, gaming, right? So you worked at gaming companies, which, by the way, now gaming companies are big users of some of these ML, particularly RL tools. And then, secondly, at Google, you worked on data, basically, kind of data ops for Google Maps, right? Am I misreading that?
No, that's right. Yeah, I actually worked on two different projects when I was at Google, both within the Maps group. One was on the actual aerial imagery ingestion pipeline. So how we kind of like take the data from satellites and get it into Google Maps. And then the other was more of a research / applied ML role called as part of the ground truth team. And what we were doing was trying to take those same aerial images, but now extract, interesting information from them. Like, for example, where's a road, or figure out where, lakes and things like that happen to be based on imagery and GPS data.
But for the purposes of this conversation, for our listeners, what's interesting about Travis's background is he's seen ML from a more practical perspective, meaning it actually gets deployed in multiple settings, and most recently at Uber. So let's jump into Horovod. So tell me about what was the genesis? What is the origin story of Horovod?
Yeah, so the origins of Horovod go back to the early days of the self-driving car group. And so at the time, the situation was that they were training these TensorFlow models in their data centers, but they were only being able to train on basically one GPU at a time, right? And so the situation was that for these very large models with like massive amounts of data, they're taking sometimes days or even like weeks to train to completion. And so the original kind of thought was, well, TensorFlow has this framework called parameter servers that exists. I remember having used it a bit, on that project that I mentioned back at Google, and that was pre-TensorFlow. That was pretty much all we had. And the problems were mostly like there were a couple of problems. One was that it was very counterintuitive. Like you had to kind of couple your training script very tightly with the infrastructure in terms of like, what parts of the model were going on which parameter servers and things like that. And the performance also was not where we wanted it to be. So, you had these parameter servers that kind of introduced an additional network hop of communication that were bottlenecking things. And so Alex Sergeev, who was the tech lead at the time, came up with this idea after reading about Baidu's work on the ring-all-reduce algorithm applied to distributed learning of, can we take this idea and apply it to TensorFlow and PyTorch and kind of make that into a more general solution. And it turned out to work really well.
Travis, for our listeners who don't follow these things closely, so why weren't TensorFlow and PyTorch themselves providing these tools?
So as I said, TensorFlow did have a package available at the time, but it wasn't based on all reduce. It was based on this parameter server architecture, which was a little bit different. PyTorch did not have anything that I'm aware of, like in the distributed training space at the time. This was kind of going back to like 2017-ish time period, right? Which isn't actually that long ago, but in ML terms, it was a long time ago. Right? So yeah, I mean, the basic explanation is that there just wasn't really sophisticated tooling around at the time, and this idea of using kind of these HPC techniques, high performance computing techniques like all-reduce, was kind of a novel idea. Like Baidu was one of the first ones to like actually seriously explore it, and then Horovod was, to my knowledge, the first open source framework to actually take advantage of it. And then later, NVIDIA's Nickel got integrated into Horovod, and this library allowed you to do very fast all-reduce on top of GPUs without having to do any kind of like copy of the data into host memory. And it just made everything a lot faster. And the end result was that now this has become kind of an industry standard way of doing distributed training.
Yeah, and as I recall, actually, Horovod, as soon as it was released, it clearly filled a need and void, right? So there was actually a good reaction to it right away.
Yeah, that's right. I mean, the project has been very successful, I think. We're over 11,000 stars on GitHub now, as well as, at this point, pretty much all of the distributed training frameworks out on the market kind of borrowed their APIs and their kind of design principles from Horovod to some extent. Like PyTorch's DDP, distributed data parallel, has a very similar interface, for example. And so I think it's definitely kind of set the course for, what a good clean API looks like for distributed training. So I think that will be its legacy in a lot of ways.
And so you started out inside Uber building this for the autonomous driving group, which was more, I would say, more researchy, right? So did Horovod become more mainstream inside Uber in terms of actually getting used by people who deployed services that people use on Uber itself?
Yeah, that's a great question. So the history of deep learning at Uber started with the self-driving car group, of course, as I mentioned. But in sort of mainstream Uber, what we called Uber Prime, the sort of situation was very different. The vast majority of models deployed were tabular models, and specifically XGBoost tree-based models. And to this day, the vast majority are still tree-based models. But what we've been seeing over the past couple of years, as new model architectures like wide and deep and TabNet become popular, a slow but steady and increasingly paced shift towards deep learning models as alternatives to XGBoost, right? And so Piero, who worked on the Ludwig project, that I'm sure we'll talk about him a little bit later, like he was one of the first.
He's been on the podcast, yeah.
That's right, yeah. So he was one of the first people at Uber to actually deploy a deep learning model outside of the self-driving car group within Uber Prime. And that was the CODA model. That was the one that did customer ticket triage and classification that used Ludwig to do the training of the model. What we've seen since then is that we've seen a increasing interest in using deep learning to apply to these tabular data sets and using Horovod as a way to scale up the training, because even though it's tabular data, we still have hundreds of gigabytes, terabytes, tens of terabytes, et cetera, of historical data that we can use. And now the challenge is figuring out, what do we need to rethink about the process, both in terms of the existing Michelangelo platform that existed to actually train models and deploy them into production to accommodate kind of this deep learning first paradigm, but also what do we need to rethink about the way that we do distributed training in order to accommodate this new tabular use case and scenario. And so that's been a big part of our focus on Horovod recently, is thinking about how Horovod needs to adapt in order to accommodate an increasingly production-oriented workflow.
So based on your experience, Travis, so you mentioned that in Uber, most of the incumbent models were tree-based, specifically XGBoost. So what was the criteria? So at what point does someone say, okay, deep learning is good enough? So deep learning obviously has its downsides. One, it might be less efficient or more black boxy. But at what point do they make that decision? Is it because the performance of deep learning just blows away the performance of XGBoost, or being the cynic that I am, or is it just because the data scientist wants to pad their resume and say they use deep learning?
Well, in my experience, there was actually quite a bit of hesitancy of moving towards deep learning at first. And it was for kind of the reasons.
Yeah, but you have something that's working, right?
You do. But I think the way that we thought about it when I was working on the Michelangelo team at Uber was that you kind of look at different models in terms of their tier or their priority within the company, right? And so you have some models where, they maybe don't generate a lot of value for the company. It's not that big of a deal if they perform better or worse by 10%, right? But then you have some models that are high touch, used as part of like every transaction that happens on the Uber platform, and you can extrapolate this to other companies as well, I'm sure. And in those cases, if you get like lift of like 0.001% on whatever metric, right? That could be millions of dollars, tens of millions of dollars in additional revenue, right? So even if it takes a lot of time and a lot of human resources, it's worth making that investment. And so what we observed when looking at the state of the world with as it pertains to simpler models versus more complex models like deep learning is that, over time, we saw increasingly more performance, more state-of-the-art results coming from deep learning. And it started to become worth the investment of saying, okay, let's put some people on this project, have them, work on it for some amount of time and see if we can get just any lift whatsoever on the model. And if so, it'll be more than worth it in the end, right? So that was kind of the philosophy.
So you alluded to, because of this, Horovod now has to position itself as more friendly to people deploying to production and more in line with the tools they're using and so on and so forth. So what has that meant in practical terms for those of you working on the project? Like what features and what things did you have to prioritize?
So there are two things that I think are different about doing machine learning with a production-oriented mindset as opposed to a research-oriented mindset. So research-oriented mindset with deep learning is you have some static data set that you're training on, right? And so when you want to do distributed training, you just spin up some VMs or some containers, and you load that data into the workers, you train a model, and then you write it out. And then, you maybe like look at the metrics and see how it does, right? And then potentially you deploy that model in some sandbox environment, right? Like maybe to a car or maybe to, some Flash server or something like that. Production-oriented deep learning is a bit different for a couple of reasons. One is that oftentimes the data that you're working with is not a static data set that exists in, some like location in a distributed file system. You're often reading from, some data warehouse or some other source of truth that is constantly evolving and constantly changing. And so really the way that you think about data being fed to your training process is actually more of like a pipeline or a series of transformations, right? And so historically, on Michelangelo, for example, what we would do is we would read the data from the warehouse using Spark. We would join that with the feature store, which is Palette, right? And then get the feature enriched data. And then we would do additional transformations using Spark, doing things like normalizing numerical values or indexing string features into numerical feature to categorical indices, right?
But everything you're saying right now is all data engineering, data transformations, no Horovod yet, right?
Not yet, yeah. But then the question is, okay, now how do you feed this Spark data frame into the training process, right? And so that's where things get a little bit ugly because now you have this heterogeneous infrastructure boundary, right? Where you have Spark on one side and you have Horovod on the other side. And so what we have historically done is we take that data frame and we spill it to disk as a Parquet file, and then we load up Horovod workers and we do the training on it. And then we generate a model, which we then pickle, serialize, and send back to the Spark driver in order to construct a servable pipeline, and then we serve that in Michelangelo, right?
But is this all what you described? Is this offline or is this supposed to happen in real time or what?
Typically, this would happen on some retrain frequency, like once a day, once a week, something like that, right? Now, the problem there are a couple of issues. One is that this kind of necessity to go from Spark world to Horovod world introduces a lot of overhead, right? You have two different systems you need to maintain that have very different resource requirements and very different kind of DevOps profiles, right? And you also have this very hard boundary between the two that is this kind of need to create this materialization of the data. And so what that means is that now you have to introduce like some outer layer, like Airflow or something like that, that's responsible for coordinating this work. And any optimizations that you want to do on the end-to-end pipeline have to be done kind of independently on the Spark part and the Horovod part, because there's no very nice, clean way to kind of fuse the two into a single kind of single pipeline, right? And so this was one of the first issues that we ran into. And specifically, this reading from disk issue for very large data sets imposes all sorts of other problems with tabular data. The batch sizes that you can feed into a neural network for tabular data tend to be orders of magnitude larger than for text or for image data in order to saturate the GPU, right? And so in order to, make this efficient, you end up having to read huge amounts of data into memory to then shuffle it, because you want to avoid, running into situations where the model doesn't train very well because you haven't shuffled the data. And then these shuffling operations end up becoming extremely expensive to do because you're having to do so many of them on such large arrays of indices, right? And so all of this stuff needs to be rethought as you start to move into more of like a deep learning first production workflow. The other component there is on the serving side. So for a company like Uber, the way that we did serving was not what I think a lot of companies do, where you just sort of take some Python code or some, and then serve it in like a Flask server or something like that, right? Particularly for models that are used in what we call real-time prediction scenarios, right? Where you might imagine a user clicks something on the app, and then that needs to be an instantaneous response from the model. In those situations, you need to serve the models using something that's a bit lower latency, lower memory footprint, right? Because we had lots of these models like that need to be served at once, right? And so Michelangelo team, they wrote a very sophisticated online serving pipeline that was based on extending some of the APIs from Spark, but it also meant that you had to make sure that your feature transformations were conformant to this like Spark-based transformation pipeline, right? And similarly, it meant that there was now a barrier, once again, like we talked about the barrier during training time, there's now a barrier for the feature transformation that happens at serving time, which might happen on some set of CPU workers. And then you're going to have a separate worker that needs to do the prediction of the TensorFlow or PyTorch model, right? Because that's served, the former is served in Java, the latter is served in C++. They don't talk to each other very nice. And so now even if you serve your model in GPU, your feature transformation is all happening on CPU. And so you're going to be bound by that part.
Right.
So this was yet another thing that we had to kind of rethink is like, okay, how do we actually fuse these steps together so that we can serve this as a single model on the GPU that doesn't have any kind of like Spark-based transformation happening, right?
So everything you've described so far, you folks were encountering as you're trying to make this work, but did you actually go to production with this combination of tools?
The state of the world was that we did end up having some models served in production using exactly that situation I described,
right,
but with performance challenges, right? And so this is something that we, and when I say we, since I no longer work at Uber, I mean like the larger kind of Horovod community, right, has been trying to tackle for a while now. We've been making good progress collaborating with the Ray team, for example. So so
does Ray seems to address some of these things, right?
Yeah, absolutely. So when I was the tech lead at the deep learning training team at Uber, one of the things that I did was to shift a lot of our platform off of this kind of like bifurcated Spark/Horovod model into kind of like a single Ray-based model, right? So the goal was to get to a point where feature processing, distributed training, all of this happens in kind of a single Ray-based pipeline, right? So you can get rid of these separate stages. You can do more optimization between stages, right, of feature transformation and model training. and then also fusing these steps together into like a single graph definition that we can then serve as a single entity for real-time serving as well. So this was kind of the big area of focus, and
and then you keep Horovod, the Horovod API for your training.
Yeah, so the Horovod API can exist as it is for training, but the important distinction is that we need to expand the scope of the Horovod API to encompass more of this data processing and data ingestion as well. So the idea there being that if Horovod can have kind of a native way of feeding data to its workers that maybe builds on top of some of the Ray APIs, like the distributed, object store, or by having like a separate pool of workers that like is responsible for reading and processing data, then that allows you to more elegantly overlap those two steps, right? Because ideally, whenever you're doing distributed training, your ultimate goal is to overlap as many things as possible, right? So you want to overlap all of the GPU utilization with some CPU usage, which is typically going to be your data loading and data preparation pipeline, right?
And so you folks recently wrote a post with Richard at Anyscale, I think describing basically what you've been alluding to, correct?
Exactly.
So it seems like at least it's partially been, deployed, right?
That's right. Yeah. So the state of the world, the last time that I was working at Uber was that we had Ray working for doing a lot of the Horovod distributed training. And we had proof of concepts in place for using Ray for doing some data processing as well, and for doing hyperparameter search. And with the kind of long-term vision being to kind of consolidate all these things together into a single piece of infrastructure.
Right. Which actually, as you described, not only simplifies the maintenance and the administration, but you gain a lot of performance benefits, right?
That's right. Yeah. Ultimately, I think that solving these sorts of data loading challenges that I described, for example, requires kind of a new type of distributed system in place that can do this kind of workload, right? And one of the nice things about Ray is this flexibility to be able to say, okay, well, I can maybe spin up some Ray actors that do this exact type of data loading and data shuffling work for me. Whereas in the olden days, it would have been a lot more daunting of a thing to say, okay, well, I'm going to write a whole new distributed system to do data loading, right? And how am I going to spin it up alongside my Horovod workers, right?
So you describe it from your perspective, Travis, but what does this work? How does this work impact a machine learning engineer or a data scientist at Uber? It must also simplify their work, right? Because before they had to use Spark for this and then switch over, and there's a lot of context switching before, right?
Yeah, well, context switching was one aspect of it. I would say that to some extent, we tried to write frameworks and APIs that abstracted that from the end users. But what did end up happening was twofold, is that one, the separation was a big concern from a maintenance standpoint for us as the platform owners, but it was also a performance hindrance for the end users. So end users would observe very frequently that this kind of barrier between Spark and Horovod, so writing the data, reading the data from disk, this whole part was very often the single point of failure for the performance of your system, right?
So when you talk to data scientists using the platform afterwards, what was their reaction?
Well, certainly there's been a lot of interest in continuing to expand the use of Ray. And even beyond just the situation I described of like performance improvements, there's a lot of interest in using, for example, RayTune to do more sophisticated hyperparameter search, or being able to use RLlib even to do some reinforcement learning applications. So there was definitely a lot of interest in it. Another aspect of this that I would say had a really good reaction was on the open source side. So one of the first kind of now proven applications of this kind of end-to-end ray-based machine learning workflow system has been the Ludwig project that I also work on with Piero Molina. And in that project for the 0.4 release, the most recent release, we specifically had the whole release built around this idea of building on top of Ray for doing hyperparameter search, distributed data processing, and distributed training, so that the users can, with zero code changes, just kind of run their deep learning training on top of an existing Ray cluster using Ludwig, right?
Yeah, I'm a big fan of Tune because the API is quite simple, and then it seems to have a pluggable backend. You can use all sorts of other hyperparameter tuning tools using kind of a single API.
That's right. Yeah. So maybe to quickly give a little bit of context on this work for Ludwig. So Ludwig is an open source deep learning framework that kind of has an AutoML focus. You could call it an AutoML framework in a lot of ways. I also like to call it a declarative machine learning framework, which is to say that you just tell Ludwig what your inputs are and what your outputs are, and then under the hood, it does all the magic of figuring out, what's the best way to train the model to give you the best performance, right? And so to do that, we have to build quite a lot of sophistication into how we do hyperparameter search. And one of the things that's, I think, very appealing about Ludwig to data scientists is that, unlike some AutoML frameworks that just try to abstract everything away from you, with Ludwig, you can always drill down into more and more levels of detail. So if you want to say, I want to use a very specific hyperparameter search algorithm because I happen to know about it, I know my data, I know it's going to work really well, we need to be able to expose that to the user through the config file that they use to do their training. And so with RayTune now, we've dramatically expanded the number of hyperparameter search strategies that we provide in Ludwig. And so now all of these are now compatible with our existing Ludwig framework for doing training. And that's been a really powerful feature for our users.
So you're closely linked to two of these popular open source projects, Horovod and Ludwig. So any updates for either one, like or even near-term roadmap for either one?
Absolutely, yeah. So on the Horovod side, as I alluded to, the biggest focus right now is on solving some of these end-to-end performance issues. So figuring out how we can more efficiently scale up the data pre-processing and data ingestion into the workers for particularly these large tabular data sets. That's going to be a big focus of the upcoming release for Horovod. Also, elastic training is one. So this was a big part of the blog post that we did with Richard at Anyscale. So we did a lot of work to enable this kind of fault-tolerant auto-scaling training, distributed training on top of Ray. And the next step is we want to expand this to support dynamic, I guess what you would call dynamic sharding of the data as well, right? So as workers come and go from the system, you want to very elegantly redistribute the data to the workers that were added or shift away the data from the workers that were removed. So this is all stuff that we're focusing on the Horovod side, as well as more general features like how can we better do model parallelism baked into Horovod as well, right? So for very large models that need to span multiple GPUs, can we take some of the ideas coming out of, for example, Microsoft Research recently to apply those to Horovod as well to help our customers? So that's on the Horovod side. On the Ludwig side, kind of two things that we're focusing on very heavily right now. One is we just wrapped up the work on Ray integration. And so now we have kind of end-to-end distributed, like large data set training, distributed training on top of Ray within Ludwig. So now you get AutoML on arbitrarily large data sets with arbitrarily large numbers of GPUs and machines.
That's awesome, yeah. Declarative too. Yeah.
Exactly, yeah. So now it's like you get this whole machine learning platform in a box with like one line of code and no need to know anything about infrastructure or any of that stuff. And now the next step is to take that even further by adding some of these new ideas, such as elastic Horovod. Richard from Anyscale did a lot of really great work on integrating Horovod with RayTune. So now we can do distributed hyperparameter search as well. So that's going to be another big area of focus for us on Ludwig, is deepening that integration with Ray so that we can take advantage of even more performance enhancing features. We did an integration with Dask on top of Ray. That's kind of how we're doing our distributed data processing now.
Right.
And we also want to expand that to Modin in the future as well. So that's another thing. The other big area of work for Ludwig right now is on, actually, I'll call out two others. So we also have the PyTorch migration that's ongoing. So we have an experimental version of a PyTorch backend for Ludwig now. So currently Ludwig is primarily TensorFlow 2 based, but we've seen a lot of interest in moving to PyTorch, which we think will give us a lot of really exciting new capabilities in terms of adding new types of trainers and new I think just the PyTorch ecosystem in general has a lot of really awesome libraries that we want to take advantage of. So that work is ongoing, and we hope to have it fully in production very soon. This will be for the 0.5 release. And along with that, we'll be able to compile Ludwig models to Torch script so that you can do this kind of end-to-end serving that I described before, where you don't have any need to kind of separate your pre-processing from your inference of your model itself. You can do all of them inside a single model artifact that can be served on top of the GPU, can be served in a C++ server, so you don't have to worry about Dockerization or anything like that. And then the last thing I want to call out on the Ludwig side is we're doing a lot of work on improving the performance for tabular data. So in 0.4, we released support for TabNet as a model architecture in Ludwig, so that you can do state-of-the-art tabular data training. And we're planning on expanding that work even further, as well as supporting time series forecasting as well, which was a recent addition to Ludwig in 0.4. So forecasting and tabular data more generally are going to be two big areas of investment in the near term.
So a quick question for our listeners who aren't familiar with Ludwig. Travis, does it make sense to play around with Ludwig even on a laptop, or does Ludwig only make sense when you have a cluster?
Great question. Yeah. So Ludwig is actually a really great tool if you only have access to a local machine. So before the 0.4 release, Ludwig was primarily kind of a local machine tool. So we didn't have any support for processing data sets that didn't fit within your local machine's memory, for example. All that's changed with 0.4 now that we have the Ray support and Dask on Ray, but you can absolutely still use Ludwig even when running locally. So what we've done is we've introduced this concept called a backend. And so by default, if you're not running on a Ray cluster, you'll use the local backend, which uses pandas for doing the data processing, and it does all of the training in a single process. But as soon as it detects that you're running on a Ray cluster, then it uses Ray. And so as a result, we use Dask for doing the data processing, Dask on Ray specifically, and we'll use Horovod on Ray for doing the training. So all of that happens invisibly, but it just depends on if you have a Ray cluster running under the hood or not. And then we'll figure that out and do the appropriate thing.
So the other question I have is tabular data. So you've made several statements about deep learning for tabular data. So are you speculating that over time, even tabular data will become the default there, will increasingly become deep learning? Because right now, for tabular data, most people still use whatever models there are on scikit-learn, for example, or XGBoost. And for time series, there's other libraries, like I personally, for example, still use Prophet. So is deep learning also going to eat tabular data?
I think so, yeah. And I believe that for a couple of reasons. One is that we have seen in general a trend that as more and more data gets thrown at the model, non-deep learning models tend to kind of top out a lot more quickly in terms of their performance.
So there's a kind of a critical point, but if you have small data, it doesn't pay off.
I mean, I would say that's true to some extent. Like when you're dealing with small data sets, typically deep learning models, particularly the bigger the model that you have in terms of the architecture size, the more difficult it's going to be to train it,
right,
to avoid kind of underfitting the model, right? With that small data set, right? So you do typically need larger data sets to make deep learning really effective. But I think that the general trend in industry is definitely in that direction, right? You know, more and more organizations have more data than they know what to do with, right? And so we need like models that are capable of dealing with all their data, not just a small, narrow window of the data, right? So that's one aspect of it. Another aspect that I think is important about kind of shaping the future direction of deep learning versus non-deep learning is that I think that you can just represent a lot more interesting features with deep learning than you can with non-deep learning. So with non-deep learning models, a huge amount of effort needs to go into the feature engineering component, right? So figuring out, okay, so if I have a user, like what do I care about knowing for this user? Like, do I know how many, like using Uber analogies, like how many trips they had in the last 10 days or something like that, right? And then I'll make that into a feature, store it in my palette feature store, and then use that in my model. For deep learning, you can do a lot more interesting things. Like, for example, take an entire vector that represents everything you know about a user, and then use that and then embed that into some high dimensional space and use that whole embedding as a feature in your model, right? And so now you have this very abstract kind of higher level representation of what it means to be a user, and you let the model itself figure out which combination of different facts it cares about in order to determine what that user means in terms of this prediction, right? So you can get a lot more rich information from deep learning models. Similarly, with deep learning models, you can combine tabular with non-tabular data sources in order to further improve the performance of your model. So, for example, if you want to incorporate text data into your model, one typical thing you could do with a tabular model is you have a deep learning model that maybe generates a feature vector that you then feed into your tabular model along with your other tabular features, right? But the problem is you can't really jointly optimize these things together very efficiently, right? Whereas if you have a multimodal model, which is what Ludwig provides, then you can jointly train your model on the tabular features as well as the text features or even image features to create like this truly rich set of information about what it is you're trying to predict. And I think in large part, that's going to continue to be an important direction that things go, because even if you have an NLP problem or something like that, the metadata about who's writing that text or who's speaking that thing or who's in that image, right? That's all extremely relevant information that will improve the performance of your model.
So Travis, so at Uber, you were mostly focused on the training side, is that right?
Yes, that's right.
Training, yeah. Because one of the things I've been thinking more and more about is the whole ML ops end-to-end space, and it always seems to come up that in many of these companies that when a model starts going wrong, it's really not really the model in many cases. It's some data pipeline downstream or upstream, right? So kind of the whole sometimes maybe we over focus on the model sometimes, and there's all these important steps that take you towards the actual model, and then and so then actually I don't know to what extent you've been following this MLOps space, but there's now also a lot of companies around just the monitoring of the models, which I'm trying to understand. So when you were at Uber, to what extent did you guys invest in tools for monitoring models, and why are there so many startups in this space?
Yeah, it was definitely a very big area of interest. The concept of concept drift or model drift, right? Like these things are very real, right? One of the ways that we mitigated it when I was at Uber was that make it a policy to retrain your models very frequently, right? And that in general will get you most of the way there.
So that means you have to have an infrastructure that allows model retraining to be frictionless.
Exactly.
Right.
Yes. And so that's a big part of what a good MLOps platform should provide, is this ability to say, okay, after I've determined, my model is good, I like the results, now I want to turn this into something that is automated.
Repeatable. Yeah.
Repeatable, exactly. Yeah. But of course, there are situations where that's not enough. So for example, with COVID, things were thrown into, a spiral in a lot of ways, right? Like you had models that were built on certain assumptions that are no longer
the 2,000-year flood scenario.
Right. Yeah. So now there are certainly times where you need to be able to detect, oh, hey, my model was making assumptions about demand or how people behave that are just not valid anymore. And so you need to, go back to the drawing board of okay, I need to rerun my hyperparameter search and rediscover what the best kind of architecture is for this particular problem. In general, I think that this whole space of ML ops is a very critical one going forward. Companies like Uber have invested a lot in building machine learning platforms that kind of make it possible for data scientists to productionize their work, right? But a lot of organizations don't have that many data scientists, if any, right, that are capable of doing this kind of very
and soon, because of Ludwig, you won't need as many.
That's the dream, right? So, certainly we believe, I believe very strongly that, the future of machine learning lies in better abstractions, right? And so what I mean by that is that, over time, as you see the maturity of any space, right, you end up taking things that are commonly bespoke, training loops, frameworks like PyTorch Lightning and Keras and Fast AI have done a good job of abstracting away that. And then you add higher and higher levels of abstraction on top of this until you end up with a product that can be consumed by people who don't necessarily know all the details.
So this is the model training aspect, but all of the things that go into the data pipelines, data prep, monitoring, that will still be there. But I think, yeah, the model training aspect, particularly like what you and Keras are building, are going to make it much easier for maybe an analyst who knows just a little bit of Python to train a model, right?
Or even no Python. So maybe that's something I'll be talking about at Race Summit. But yeah, so there's a really interesting point there, I think, which is that, on the data side, certainly, data, as you mentioned before, is really the lifeblood of all of it, right?
Yeah, so I imagine at Uber, when you were working at Uber, you probably learned more about the data from the people on the business side, right? Because they understand the data, right?
They do, yeah. The analysts, the business intelligence people, the business stakeholders know the most about what it is that the data really means, right? But they don't have, obviously, the data science skills most of the time.
Right.
One thing that I think has been a really interesting trend in the industry to observe has been the shift from unstructured data lakes to structured data warehouses. Would you agree? So you have this kind of...
there's definitely, if you look at the companies that are really creating a lot of noise, they are the ones that simplify exactly what you described, right? So
exactly.
Snowflake, Databricks, and whatnot, right? So.
And here's kind of the historical premise that I have for this is that, when you go back to kind of the beginning of the big data boom, late 2000s, early 2010s, right? What you saw was a huge explosion in the amount of data that was available to us, but a big lag in terms of the sophistication of the tooling that could know what to do with it, right? Know how we should structure it, know how we should index it, what types of systems we should have on top of it to do retrieval and processing. And so I think frameworks like Spark did a really good job of filling that gap of saying, okay, let's just dump all of the data to a distributed file system, and we're going to call it a data lake. And then we're going to have data scientists and data engineers use Spark to process this data into forms that are more interesting and kind of create these bespoke transformations on the data that can be used for analytics or for machine learning, right? And then over time, what we've seen in the past few years now has been a huge shift back to kind of the warehouse model where we say, okay, we've generally consolidated the types of transformations that we're doing on the data, the types of workloads that we're doing on the data. It's becoming standardized again. And so the time has come for providing a structured, declarative SQL interface.
Which, by the way, that's why there's so many of these interesting data engineering startups around data integration, ELT, ETL, right? So
I love looking at these startups like DBT that are just like rethinking the entire paradigm of how we do data transformation, going away from like the let's write a Spark pipeline to let's write SQL again, right? It's like everything kind of comes full circle back to something like SQL, something declarative that kind of allows you to express your intent, like the what of what you are trying to do.
Yeah. So if you have a lot of rigor around your data ops, which is your data pipelines, data quality, data governance, and all of this, and then you layer some tool like Ludwig on top of it, you can really unleash a lot of domain knowledge within companies, right?
Exactly. So that is where we're trying to take things, and so that is exactly what I'll be talking more about at Race Summit. And that's I think the vision, right? Is that you look at where the industry is headed. You say we're moving back towards a model where things are more structured, where analysts and business stakeholders have more of an ability to interact with data. Now let's think about how we can also allow them to interact with the machine learning as well.
Right. Yeah, because many years ago, there were these class of tools that attempted to make machine learning accessible to analysts using some GUI interface. But I just don't think companies were ready for it at that time for a variety of reasons. One, they didn't have their data lined up. And maybe those tools were not that great, honestly. Didn't scale, limited number of algorithms. But now, we're moving into the world where maybe at the hands of analysts that they can use deep learning, right?
Exactly, yeah. And this kind of comes not just from the warehouse side, which kind of is generalizing this problem of representing data and doing data quality and data updating, but you also see this same convergence happening in machine learning, right? Which is, I think, driven primarily by the transformer architecture right now. So you're seeing transformers now becoming a general architecture that's used to solve NLP problems, image classification problems, even tabular data and forecasting problems are using transformer architectures now. And so you take these two things together and you can see where the future of an open source tool like Ludwig lies, right, is in this ability to bring these things together and provide a really simple declarative way of doing machine learning on top of structured data.
But the key, as to our listeners, as Travis has alluded to, is at the end of the day, for companies, you need to really make this kind of model training, retraining, deployment, monitoring as frictionless as possible in order for you to be able to really reap the benefits of ML.
Exactly. Yeah. So you absolutely need some structured infrastructure in there as well. And so, open source tools are like a good foundation. And then on top of those open source tools, you need to have, industry production grade infrastructure, right? And so,
yeah, because in many ways, if you think about it, right, so software engineering itself has years and years of deploying. You've got books about SRE and all of this. So a lot of those map to ML, but ML itself has certain special requirements that require new tools. That's why there's all these new startups, right? Because ML is data and code, right? So there's training and retraining and data quality and all of these things. And versioning a model may mean saving a copy of the data. Well, you just don't stick petabytes of data into Git, right?
Right. Exactly.
So yeah, so there are a lot of lessons from traditional software engineering, but it is true that the companies who excel in ML, productionizing ML, have invested in kind of that next step of tooling for MLOps.
Exactly. Yeah. So, for example, you look at a company like Uber that I think has done a really good job of building out this kind of like industry standard MLOps-ish platform, right? And now the next step is to think about how this can be taken to other organizations, right, that maybe don't have as much data science or engineering expertise. And so you see lots of MLOps startups, obviously, in this space, right? And I think where I would think about it a little bit differently from maybe some of them is that instead of targeting more of the kind of data science use case, with something like Ludwig, we definitely think about like a more business stakeholder or more analyst stakeholder, right? And so that's kind of the focus for the Ludwig project going forward.
Which, by the way, for every data scientist, there might be 20 to 50 analysts.
Right, exactly. So it's definitely and I think a lot of this comes back to like the fact that these organizations have been around for a while, right? As you have organizations that have a lot of data infrastructure, and they can't just kind of completely reshape their business overnight. And so being able to leverage an existing workforce of analysts or business intelligence people to do more of this, interesting work with machine learning, I think is potentially a very powerful enabler.
And with that, thank you, Travis.
Thank you.